the video's on, and here's that creature I'm getting rid of again. So I want to remind you of just a brief synopsis of what we've done. First lecture was on probability distributions. That was kind of really a throwaway lecture. I hope you got something out of that, but it's just the first day's lecture, right? Remember last year, the first lecture was just shot. Regardless, the probability distribution, we'll do physical chemistry now. The probability distribution, how does energy get distributed in nature? How does nature distribute energy? We really can't know. You know, we have all these ideas about like modeling the motion of molecules like they're vehicles, like using Newton's equations, and that's like a whole field of science. But modeling the motion of atoms in the entire world, or even just in a balloon, would require a computer way bigger than we'd ever have in 1,000 years. So instead, we treat molecules in a balloon like they're a bunch of busy bees. They're moving around randomly. While that makes it easier to model, the loss is that we have to use this kind of inexact description. We don't know how fast things are going. We just probably know how fast they're going. So we lose a little bit on this very atomistic, you know, perfect description of the motion of things. What we gain are a bunch of equations that are tractable and get most of the picture that we want. Okay, so we're going to do that with our balloon of gas. We're going to model their velocities. I have this equation for how Boltzmann's equation describes how energy is parceled out by nature. I'm going to give that energy just to the motion of the molecules, or their translational motion. So I'm plugging in E is 1/2 mv squared. And then I also have to remember that velocity is in 3 dimensions. And I also have to get rid of the sum because velocity is continuous. And I see I've already made a mistake. I'm still not quite super comfortable, by the way, with how this triple sum in x, y, and z turns into triple integrals, because the Riemann, what's it called again? The Riemann sum equation doesn't really apply. So I'm pretty sure, I'm kind of making this up out of my rear end, but I'm pretty sure what you do is you multiply and divide by these partials. And oddly enough, this is exactly the equation in textbooks, so I think I've done that right. I just haven't found an authoritative source on that. Okay, so again, 3 dimensions, and for those of you who are, your class is definitely a little mathematical. When I'm doing 340 physical for biochemists, they haven't had multivariable calculus, it wasn't required. And they look at this and freak out, and I tell them, no, you know, multi-dimensional integrals are just, it's just 3 integrals and you just multiply them. It's like absurdly simple. So, yeah, so there's that. Okay, now the thing is, I know that this is kind of hideous, so the next thing we do is we simplify this. This is at the end of last lecture, and I was kind of rushing. I just gave you the result, and so one person even asked me, like, wait, where did that come from? So and that was because I was writing how I do that sometimes. That comes from this identity. And now remember, on the exam, you are going to have nothing but identity. You never actually have to do any calculus. I will generally do calculus in class, but I don't expect it on a test. Just because, I mean, I know it sounds like you may be thinking, oh, well, of course not. I don't know. It's kind of a struggle for me to think whether you should be able to do that. No, I'm certain you can do it. I'm just struggling whether to require that or not. And I don't, but anyway, I'm just a little afraid of the erosion of math skills. I heard that from the folks who taught me, oh, your math skills are eroding, and now that I'm that person's age, I'm saying that to you, so circle of life, zebras. Anyway, so, okay, so I have this identity, and in the next hour, I am going to do a little bit more calculus, by the way, because again, I don't want your math skills to erode. You know, math skills are the #1 indicator of your future success, by the way. Even if you go into organic chemistry, if you have a better math GRE score, you actually end up being a better grad student. So anyway, that's why I'm going to emphasize this throughout the course. All right, so let's just do one of these. And now again, remember, if you're a little bit like, oh, I don't remember my my multivariable calc, or I didn't have it and somehow you signed up anyway, which happens as well. There's nothing to multivariable calc, and even if you don't believe that, well, I'm doing it right in front of you, so that's not hard. So when it comes to applying an identity, all you have to do is figure out that A is m over 2 kBt. Okay, the limits are the same. Don't use an identity with different limits, that doesn't work. And that's really it. So this ends up being square root of pi 2 kBt, and I messed it up, there we go, over m. Okay, okay, now let me see, I see a mistake. You're going to have to do this on the homework in the exam. You have a question that's like this on the homework. Let me point out a mistake that you commonly make. Let me see if I can trick you to doing it. Is A m over 2 kBt, or is it minus m over 2 kBt?
Well, it must be positive.
Well, hold on, there's a minus right there. There's a minus there.
Identity?
But the identity has a minus too. Right, you see? Sorry, so no minus. Again, that's something that tends to get people. When people miss questions like this, that's what you did wrong. Now, a clue is, by the way, you put a minus sign in the square root. Yeah, that's a problem. So, anyway, I just wanted to point that out. Okay, now let's see. Sorry for my funky use of the board. If you see why I do like this room a little bit better, I'm going to go from the top and bring that down here. What you end up with is, okay, the top thing I'm not going to mess with. I will in the next hour, but not this hour. I shouldn't say anything because you'll understand in the next hour. Okay, these partials are still here, and these partials in x, y, and z, these are appearing as well because in the bigger picture, you can think of it in the nuts and bolts sense that I had this sum, and I had to turn it into continuous, and so that introduced those partials, that discrete, it's called a discrete probability density, and I had to turn it to a continuous probability density. So in the nuts and bolts sense, that's how they appeared. But again, actually a bigger picture is that the probability density became continuous, and that's really why. Okay, and then these guys on bottom end up being pi kb t over m. I like to put the 2 in front, and there's 3 of them. So again, there's your multivariable calc. And so this ends up being where we're almost done. Now again, just a little, I'm just doing some algebra. And I want to point out that, I mean, that look at that. I mean, I don't know you all that well. I think I would have looked at that at your age and been kind of scared, like, oh my God, look how big that thing is. And look what we got. And mostly, as much as this still may look a little scary, remember I said the first day, look, it's just a bunch of constants. And I will have you do some things with those constants, so make sure your calculator skills are up to par. And I have some guides for you to figure out whether you've messed up. In other words, if you get if you get like faster than the speed of light, you've screwed up, something like that. Anyway, and okay, so the last bit again, I just want to point out that hideous thing. This is going to happen over and over again. We have that hideous thing, and now it's just not that bad. It's a bunch of constants, and e to the minus mv squared. All right, that's really not bad. Except that we have a major problem. All right, velocity, that's net velocity. Okay, so that's the square, oh, it's squared, so I'll put it in the square form. It doesn't matter, it's the same point. The x squared plus vy squared plus vz squared. Okay, now on your homework, I have you work problems with this equation, and you plug dx squared plus vy squared plus vz squared into this part here. So remember, this is like the numerator part, this is the denominator part. I bring that up a lot. I should have emphasized that before. So this numerator part on your homework, I have you plug that in and you do some manipulations. And I will do an example in the next hour. What I don't like about that is that what we're going to do today is we're going to use this thing to calculate net velocity. So when I have net velocity here, not velocity squared, it's irrelevant, it's net velocity, but I got a problem there. See, the thing is that normally if I have like a function with x in partials of y, it's actually an incredibly trivial integral. It's just the function times y, right? The problem here is that this xy and this vx, vy, and vz, they are in here. They're right there. They're hiding in there. And that can be a major problem. I can plug this in here and do problems like you are in your homework. That ends up being easy. But if I want to do anything with net velocity, I need to keep that and get rid of that. And that is the subject of my PowerPoint. But now I want to ask you this. Who thinks that to start doing things like, probability density integrals, right? Like now, do you remember the first lecture? What if I just did this? Just wiped it out and said that. What if I just did that? You see no problem, right? Remember, the integrand, the partial is telling you what you need to be integrating on. So this says, this is the deal and it's right there. And then of course I look up an identity. That's how I would do this. My question to you is, what do you think? Do I just wipe that out and then just write dv and say, hey, I hope it works? Some of you are saying yes, no. No, I mean, I know it's tempting because you're like, well, it's all velocity. I know it's tempting, but you can't. Now, for one, it's just flat out wrong. Now, number two, this is like one of the cooler things I know. It's information theory. So mathematicians study the information content of signals, and they have all these theorems on it. I'll give you an example. You often see TV shows and movies where a signal from outer space, we got a signal from Alpha Centauri and it's this. Oh, let's improve the resolution and and stretch it out, and then all of a sudden it's a voice in the picture. It's like, we're coming, right? No, this is at best a tone, right? There's no information here. You can't do that. You can't turn a short signal into a long signal. It's just flat out wrong. Okay, look what we have here. I have 3 dimensions. Remember, I brought this up before. I have 3 dimensions, so that's 1 dimension. I'm not worried about, x, y, and z. There's 3 partials. That makes it 3-dimensional. That's 1 partial. Net vector that it is, it's 1-dimensional because there's only 1 of them. And that means that you've lost information. That means you've done it wrong. If you just wipe this out and put that there, you've gone from 3D to 1D, and that's no different than being asked to, I'm asked to describe this room. I look around and I describe the room. Then I have to look through a tube and describe the room. I'm going to get it all wrong, right? Because I've lost information. In the same sense here, if I just wipe this out and put a partial, I've gone to 1-dimensional, and I'm just going to get all the results wrong. Anyway, okay, now, for the first time, I'm going to actually PowerPoint. Oh my God, what the... What the purpose of this is, to figure out how to change the partial of Vx, Vy, Vz into the net velocity, the partial of the net velocity. How does... Let me not complicate it by making it velocity. Let me just make it x, y, z. Right? X, Y, Z. Vx, Vy, Vz, or X, Y, Z. It's the same idea. They're orthogonal vectors, right? 90 degrees. X and Y and Z are 90 degrees from each other, and so are Vx, Vy, Vz. Okay. And I'm not talking about X, Y, and Z. I'm talking about the partial of X, Y, and Z. Now, I will show, I think, I have a handout on the website, and I may bring this up next Extra Friday. I will show you a very rigorous mathematical way of going partial x, partial y, and partial z to partial net velocity. I'll show you how to do it like exactly, but there's this hand-waving way of doing it. That's really instructive, and it tells you how integrals work. And some of you folks have heard this, the other people have. You've heard me say this ad nauseum. When I'm describing a calculus equation of things that are real, then the integral corresponds to an actual action. And the reason I bring that up is that makes it actually very easy to understand. Or much easier than you think. Anyway, okay, so I want to get into more of the nuts and bolts of what an integral really is. And I'm going to start with the simplest one possible, right? One-dimensional, right? Now you notice I'm focusing on that quite a bit. One-dimensional because there's only one partial. It has to be x. Again, I'm just trying to make it easy. I just made the limit 0 to infinity just because I could draw a nice little graph. And that actually looks like a Maxwell-Boltzmann distribution. And what happens is you see that, and you're doing this also on the homework, by the way. Obviously, everything's exaggerated. Partials are infinitely small, but let's say that they weren't. You see that the partial, as you evaluate the integral from 0 to infinity, what you're doing is you're taking a finite step along the x direction, multiplying that length times the height to generate the area, and the integral is evaluated from 0 to infinity by simply adding up those areas as you step along, right? This took me hours. Let's watch it again. Why? It took me hours last time to do this. So there you go. Okay, the important thing is I just want you to see two things. We're taking little pieces and adding them together, and those pieces have a geometry associated with them. The partial is a line, and it creates an area, and the areas are added up. And you know this, right? Now you have this in Calc 1. It's also on your homework. You have a homework question like this. Okay, now this is the part, hopefully you haven't seen this before, and hopefully you think this is kind of cool. And I'm sure it is. Anyway, all right. Let's raise the bar by going to 2 dimensions. And again, x and y makes it easy for you. What I really see is 2 partials. 2 partials is 2 dimensions. Okay, x and y. X and y. So, look at that. All right. Okay, now where's the geometry that I saw last time? In this case, x and y generate an area, and that's crosshatched. The area is multiplied by the function, and just look at it. See, area? It's multiplied by the function, which is a height, and it generates a volume. All right, so we've gone from areas to volumes because we've gone up a dimension. And I didn't animate this because that's way too hard, but as you would evaluate the double integral, what you're doing is adding up all the volumes in all the different little partial squares. Of course, I couldn't animate that. That's a little too hard. And of course, the function that you see is no longer a line, but a plane, because it's also 2-dimensional. Okay, anyway, this guy's kind of important. So let's go to 3-dimensional. Remember, I'm trying to convert partial dx, dy, dz into net velocity. So I have to go to 3 dimensions. Okay, I'm going to lose one thing here. Previously, I showed you partial times function. Partial times partial times partial is now a volume, right? I can't render that times the function because that's 4-dimensional. It's kind of a miracle I can render a 3-dimensional object on a 2-dimensional board. I cannot render a 4-dimensional object on a 2-dimensional board. I could not render a 4-dimensional object on a 3-dimensional board. So, it actually is irrelevant. The point is that from the last slide, I just want you to think of these partials as generating shapes, and in 3 dimensions it generates a cube. So there you go. So, yeah. All right, now what I've done is, now think about how on the first slide, how we took steps. How we started at 0, in this case we're starting at minus infinity. We started at 0 and we started walking. And we walked along, as we walked along, we encountered different geometries. And in this case, we're starting from minus infinity to infinity, which is a fancy way of saying, here's this cube, and as I evaluate the integral, I'm going to push it forward and backward because it goes from minus infinity to infinity, left and right, and up and down. And then I'm going to go a little bit further, and that means I have to go now caddy corner, more forward, also backward, left, right, caddy corner, caddy corner, caddy corner, caddy corner. Okay, and I do that a couple hundred times, and what have I got? It begins with an S, and if you're loud, I can hear it's a ball. Right, it's a ball. Okay, so it's a sphere. Now, this is our first step to figuring out how I change partial x, y, and z into the partial net. In x, y, and z, that would actually be, well, let's see if you can figure that out. So, what is the net velocity in x, y, and z And the word, I'm looking for a particular word, and it should help you that you see a sphere. Right, what is the square root of x squared plus y squared plus z squared?
Oh, the equation. Root means squared?
Now, you're looking at a sphere, so think of a word for the net x, y, and z.
It's a radius. Huh?
It's a radius. Right, the radius gives you the length of the vector, right? R is square root of x squared, y squared. I hate to admit, I'm a little bit perturbed that I have all these v's and x's. I'm afraid it can throw you off a little bit, but I hope not. Anyway, okay, so now what we're going to do is we want to see how this volume grows as the net vector, the net length increases, right? So I've represented that here by putting more spheres forward, backward, left, right, catty corner, yada, yada, yada. Okay. Now the question is, I want, this guy shows me how the volume of the partials changes as I look in x, y, and z. That's great, but I want to not do it that way. I want to look at the net change. I want to look at the partial of r, right? So I can know the partial of r, but how does the volume change? That's the question. So if I can multiply the change in r times the change in volume, then I've given the same thing as partial x, partial y, partial z, right? So again, get rid of x, y, and z and replace it with r, but it also has to provide that information of this volume growth. It has to do both, right? I have to be able to throw in change in r, but the change in r also has to give me this blue volume. Now, this is going to be a little bit easier if I just kind of give you the answer. You'll figure it out. I think you may be I see a couple of you going, wait, what? Okay. What is the volume of the blue squares? And let's just call them spherical, right? I know it's coarse grained, but they're obviously spherical. Now, I didn't show the top half, right? I want you to see the smaller sphere and the bigger one. The blue is actually all over the place. So what's the volume of it?
Just the blue spheres.
Just the blue spheres, right?
So it would be 4/3 pi parentheses r plus dr 4/3 pi r cubed, yeah. Right, minus 4/3 pi r squared.
Right, it's not the volume, the blue is not the volume of a sphere, it's the volume of a shell.
Yeah.
That's what it is, the volume of a shell. Right, now here's the point. I can replace partial x, partial y, partial z with partial r as long as partial r also communicates that shell volume. Because if it does so, then it's correctly mimicked what partial x, partial y, partial z do. Okay, now your formula was slightly complicated. There's a slightly easier way to do this. Textbook, I had to show it. All right. So, okay, so this is what we're trying to do. Figure out how that blue volume, what's that blue volume? Okay, now looking at this guy. Now remember that the growth is infinitely small technically, right? What is 4 pi r squared for a sphere?
Surface area.
Surface area, okay. Now think back to the second slide, when I had an area times the height gave me a volume. Surface area times change in r, which is the thickness, gives the volume. Right. The volume of a shell, a spherical shell, if the shell is thin, which this one is, these are partials, is the surface area times the change in r. What that means is partial x, partial y, partial z turn into 4 pi r squared. Change in r, right? But remember, the whole point was change partial x, partial y, partial z into partial r. The point of all of this, is, especially if this was confusing, was that it has to have that 4 pi r squared with it. Otherwise, it doesn't scale correctly. It doesn't scale as a shell volume, and hopefully all the blah, blah, blah I've been doing is convince you that it should do that. Note also that x, y, and z in the function also have to go away. I have to find the r there too. So there you go. And also these are figures for the book, and I will have that to you at some point so that I don't leave you hanging. And there you go. Oh, God, that's I didn't realize. Anyway, okay, so That's my PowerPoint. So you can see why I wanted to PowerPoint this, because when I tried to draw that, I mean, you know, I don't think it was that bad a drawing, but you gotta be kidding me, right? So, so anyway, that's why I did that. And now let's move on. And what do we do next? Okay, so now what I have is I'm just going to write out the real Maxwell-Boltzmann equation in the net velocities form, and then you have that. And then we're going to start to do all kinds of tricks with that. I'm going to show you some neat things with statistics that transcend the specific example of how fast is a gas moving. I mentioned I'm going to try to do that because it may not be so interesting to you how fast is a gas moving. Anyway, so here's Maxwell-Boltzmann, and I'm writing this as a function of net velocity. And what I've got is a 4 pi r squared. I like to put that up front. And I've noticed that the video resolution is not so good, and I don't know why that is. I don't know if that's because the camera's getting old or if YouTube is doing some things. Okay, 4 pi r squared is this geometry factor. Then I've got m over 2 pi kVt. Remember, this is the normalization part from the Boltzmann equation. On exams, I have at times written out the Maxwell-Boltzmann equation and asked you, just describe why is this there, and I'm doing that right now, by the way. This is the numerator of the Maxwell-Boltzmann equation, and now we're left with the partial. And you notice it also has the correct form of a probability density. It's some function, and I got myself a partial as well. So I need to have that. That's the spread. And you see that I'm also, there's nothing I can do with this unless I don't integrate it. I can graph it. I'm going to graph it and show some things, but anyway, question.
Should it be partial log?
Or
does it stay?
Oh, sorry, God, what is wrong with me? I'm sorry. Now, remember I was saying I was a little, like, for one, it doesn't help when I write it wrong. I wanted to show you that geometry in X, Y, and Z because you're used to X, Y, and Z, and of course R, theta, and C, and all that. But in Maxwell-Boltzmann, it's Vx, Vy, and Vz. Instead of an R, I've got a V. So that's why, and I confused myself as you just saw. So I'm not quite sure how to do that, right? I know you're so used to X, Y, and Z, and it doesn't matter that it's Vx and Vy and Vz, but so I'm not sure whether I should have done what I did and put everything in X, Y, and Z, or anyway, follow it down anyway. Okay, so, but we're okay, right? The main problem is I wrote it wrong. All right, now, here's the thing. What we can do is we can do some graphs and show you what this thing looks like, and then we can do some calculations. Now, I mentioned that there's some minutia in terms of what you get out of this. You plug in constants. I plugged in O2, so this is Maxwell-Boltzmann distributions for O2. I plugged in a temperature of 25 degrees, and these are in meters per second. Sorry, I backed myself into a corner here. Yeah, maybe I should have just put these graphs up instead of trying to draw them right now and after drawing data. So the Maxwell-Boltzmann spikes like this. And that's at 25 degrees. Okay. As you warm it, it doesn't change much. It doesn't seem to change much. It gets a little wider. That's 100 degrees. And then if I go to 200, it's just really not that different. So temperature doesn't have a really big effect. And that's 200. Now the neat thing is, does anyone know the speed of sound off the top of their head? What? 344? That's 344? No, 343. How the hell do people know that? You looked it up before class, didn't you? Yes. I looked it up. I don't know that stuff. I always joke, I think I told you this before, you know, I always joke that one day I'm going to have a test and it's going to be about what's the distance of the Earth to the moon or something. no matter how smart you are, you're not going to get that right, but maybe you will. Anyway, so, okay, so notice that the effective temperature is not that great, and notice how fast the damn thing is moving, right? So speed of sound is here, and for the most part, a lot of the molecules, most of the molecules are moving way faster. And I think that's kind of this neat fact about Maxwell-Boltzmann, and that's about it. The other thing that we're going to do, what we're going to do from here on out is going to transcend that little factoid that I just mentioned. Just give me 1 second. I want to show you the effect of mass, which is like absolutely insane how much mass matters. So again, this is velocity, Maxwell-Boltzmann. If you have something that's heavy, it looks like this. This is xenon hexafluoride. Mostly it's solid, but it sublimes quite readily, so that's a gas. Here is O2. And what's really cool is helium. So O2, the example I just, and these are at 25 degrees C. And this is helium. So here you go. Actually, I do know. I know one other kind of interesting little factoid about this Maxwell-Boltzmann stuff that's kind of interesting. Okay, so helium is, so the effective mass is just unbelievably large. And helium is moving insanely fast. In fact, you can calculate what is technically escape velocity for the planet, right? You know, the space shuttle rockets have to get this fast. And if they get this fast, they can escape Earth's gravity and keep going. I've forgotten where that is on here, but helium is, for the most part, well above it. So guess what's happening to the world supply of helium? Yes, we are literally losing it to outer space. I am not joking. The Earth supply of helium is dwindling. Do you know where we get it from to begin with? Here's a hint. Almost all of you are going to be working in this industry. It's the petroleum industry. It is the petroleum industry. It turns out when you dig out oil, helium gas just evolves out of it. They capture as much as they can. We use it. We accidentally will vent it, and then it's gone forever. That is literally how we use helium. The problem with that is that's how your MRIs work. As soon as you run out of helium, no more MRI, and you're all going to immediately die. So that's a little scary. Okay, anyway, next bit. Next bit is, these are nice little factoids, but what I want to do are averages. Okay, so so what about this? Well, we can calculate the average question.
Is that the same thing with hydrogen? Since hydrogen is like
hydrogen is, wait, so hydrogen is lighter, right?
Yeah.
Yeah, so hydrogen, the thing is that the Earth has tons of hydrogen. It's just locked up into H2O. It's not impossible to get that out. But helium, we can't do much about, right? So, okay, now averages. Now here's the thing that transcends just the stuff I talked about, helium and how fast they're going. Averages. Average of 5 numbers, what do you do?
You take the amount divided by the number.
No, that's actually wrong. The way you learn how to do averages, taking a bunch of numbers and adding them up, is a limiting form. Adding them up and dividing by the number of numbers, that's a limiting form of a distribution that's flat or Gaussian, or bell-shaped. It doesn't always work. The true definition of an average is the integral over all values times the distribution times, of course, times a partial, which, remember in my little parlance before, y is the property. This is the, sorry, no, you know what I just drew? Yeah, what is this? Anyone know what that is?
It's a probability.
Yeah, that's the number 1. Sorry, I'm just, I'm speaking off the cuff, I just made a mistake. There we go. You take the probability distribution times the thing it's a function of, times the partial, integrate over all values, and that's the average. And this would be the average of property y. So I just want you to remember that this is how you properly express averages in our math notation. So it's important that you know that. Anyway. I don't know that I can prove this, it's just it is. But this whole idea of taking up a bunch of numbers and averaging them and dividing by the number of numbers, that depends on the shape of the probability density. It doesn't work for all things. Now, it does work when you have probability distributions that are top hat-like, flat, that's like for picking dice out of the bag. Grades, which are bell-shaped, those work just fine. But Maxwell-Boltzmann, you may notice it here, it's skewed. It's got a skew. It's almost bell-shaped. It's almost bell-shaped, and that's coming from here. But this is screwing you. This is causing it to slant to the right. And that changes everything. So not only is this the proper way to do this, your notion on how to do averages is not necessarily correct when you've got a skewed situation. All right, so we'll do this for velocity and and here's another thing that's kind of cool. You can actually ask other things. You can ask, like, what's the average velocity squared? All right? Now you may think, oh, wait, why would I do that? Let me show you something real quick. Why would I do this? Why don't I just get the average and then square it? You can do this. I used to have people do this on homework, except that I realized it was stupid. Here's 3 numbers, and the average is 5. Right? 10, 15, 3, 5, right? Okay. Now let's square them. 25, 49. Sorry, I don't know. 49. The average is 27.7, which is of course not, which is bigger than 5 squared. So numbers, this is just what they do. Okay. Now the point being is that not only, we always think of average, in this case, oh, what's the average speed? I can also calculate the average speed squared. And I have to do this as a separate calculation because of what I just showed you here. The average of the square of the speed is not the same as the average squared. I'll show that in a graph because I know what I just said is probably kind of confusing. Anyway, real quick, what I have on the handouts, by the way, I have 2 handouts on calculating average velocity and average velocity squared. And I've done them very long-handed without an identity. And so that's for you people who, if you really want to see how that's done, you have to use, what do you call it? When you, God, I'm just getting older. Partial, no. God damn it, what the hell is it when you do this? No, it's, what the hell is that called?
Separation of areas.
Separation of, no. Integration by parts. God, what is wrong? I'm going crazy there, thank you. Anyway, you have to do it by integration by parts. But I just realized that I don't want to spend that much time doing integration by parts. I think you should be able to do it. And if you have any trouble, look at the handout. But what I'm going to do is, because this is what I have on the test, I want to just do identities. Because why not? Okay, so the average velocity is going to be the integral of the velocity times the Maxwell-Boltzmann distribution of velocity, dv. Now, this is a part of your exam and homework. You got to get the limits right. You got to get the limits right. Okay, net velocity. There's no negative net velocities. They don't exist. 0 is your lower limit. Your upper limit is infinity. If I was doing this with respect to x, y, or z, dx, vy, or dz, the lower limit would be minus infinity. I'm going to do an extra problem in the extra hour to emphasize that, so I'm not going to leave you hanging. Anyway, all right, so what is this? You know what I'm going to do? I am actually going to take a lot of the constants, and I'm going to put them outside the integral, because they're just distracting. And I don't need to worry about them. It's just a number that I'm certain I can use my calculator. Okay, the real part of the integral is here. Now, notice that there is a v squared. Notice that there's a v squared times v, which is a v cubed. So don't get thrown off. Remember, Maxwell-Boltzmann has a v squared, but I've multiplied it by a v because I'm trying to get the average. I'm going to call this just a little q. It's just a bunch of constants. I'm just going to call them a q, and then I'm going to forget about them. Okay, you're at the exam, now you're looking for an identity. Here's an identity. I could write up a couple. And I've told you, for you folks, I give you identities that I Google these, and I give you the first one I find. When I Google Gaussian identities, this is the one I found, and that's what I give you. Okay, and this is 1/2a. Okay. Don't forget the limits. Now, when I try to distract you on exams, I give you identities with different limits, because that's what I find when I Google, and I'm going to throw that at you too, and that's fair. You should be confident enough to notice that, all right? So that's it. Okay, so what I've got is Q, 1/2, up here. A is, just like last time, it is M/2 KB. Okay, so this ends up being M squared 4 KB T squared. Now, I work it on the handout. On your exam, the number one thing you forget is the prefactor. Don't forget the prefactor. Don't just write this down, that's not the answer. The real answer is 8 KB T over pi M. That is the real velocity. All right. It's a mess, and I won't have you do it on the exam. In fact, if you wrote this on the exam, I give you full credit. You've clearly defined this. You got the right identity. You used the right identity. This is correct. You don't need to simplify it. I just like to simplify it because it's so there you go.